In this demonstration, we'll see the Synopsys controller operating in FLIT mode at the new Gen 6 data rate within a simulation environment. On the screen, we can see the Synopsys Core Consultant GUI. The GUI enables the user to select from a wide range of configuration options and features. The current window is showing the configuration options for the maximum supported link speed. For this demonstration, we've selected Gen 6 as our maximum speed. And we can see at Gen 6 speed, the controller will operate with 64 bits per lane at a frequency of 1 GHz. This slide is showing the verification environment that we are executing for this demonstration. On one side of the link, we have the Synopsys DesignWare PCI Express controller with the Synopsys 64 GTS PHY model. On the other side of the link, we have the Synopsys DesignWare PCI Express verification IP. Both devices on the link have been configured to support Gen 6 speed and protocol, and the test bench will generate and monitor the link traffic. Here we're showing the waveform from the simulation of the Gen 6 controller. Both sides of the link have negotiated FLIT mode, and we enter L0 at Gen 1 speed with FLIT mode negotiated. We then proceed to Gen 3 to perform equalization at Gen 3 data rate. We move on to Gen 4 data rate and perform EQ, and also repeat at Gen 5, before finally performing equalization at Gen 6 rate and getting link up into L0 at Gen 6 FLIT mode. When we enter L0 at Gen 6 speed, both devices will exchange sequence numbers using sequence number handshake state. We start transmitting, or we can see the controller transmitting its sequence number and acknowledging the received sequence numbers from the PHY. And the same is happening on the RX path with the FLITs that we're receiving from the controller. When sequence number handshake completes, we go on and complete FC initialization and bring the link up DL active. If we zoom in at this stage into the signals on the PHY, the TX and RX lines, we can see that the unit interval is 31.25 picoseconds. And as we're running in PAM4, we've got 2 bits per unit interval, equating to our 64 GTS data rate. Following our link up into L0, we then start to exchange TLP payload FLITs between the 2 devices. Here we can see the signaling on TX and the RX side to indicate that the FLITs we're receiving are containing payload. We can also visualize the FLITs in the simulation by looking at our FLIT transaction log. Here we can see details on received and transmitted FLITs. We can see the type of FLIT, payload, no-op. We can see information on the DLLPs that are contained within the FLITs. We can see the CRC and FEC values that each FLIT is carrying. And we can also see the TLP content that is being contained within each FLIT.
This demo showcases Synopsys PHY IP for PCIe Gen 6 in 5 nanometer process. Here we can see PHY test board in its characterization setup transmitting a 64 Gbps PAM4 data pattern into the real-time oscilloscope. We will zoom in on the oscilloscope screen for a closer view. The transmitter eye diagram has well-balanced and open PAM4 eyes due to transmitter's low jitter and high linearity. The next setup demonstrates the PHY in loopback over PCIe Gen 5 compliance-based board channel. For this test, we are choosing a channel with total loss of 32 dB to match PCIe Gen 6 standard maximum loss guidelines for receiver testing. This channel includes reflection, non-linearity, and discontinuities, which makes it more difficult channel compared to a higher loss channel, which is linear in nature. This part is bought out of reset and initialized into 64 Gbps PAM4 loopback. PRBS 31Q pattern generators and matchings on chip will be used to calculate bit error rate. We will speed up the video to show our continuous bit error rate readout. On the left is a plot of bit error rate versus time for 32 dB loss link. The PHY exceeds PCIe Gen 6 target bit error rate specification of 1 e to the power minus 6 by 2 order of magnitudes consistently over time, and we achieve 10 to the power minus 8 bit error rate. On the right is Synopsys patent pending non-destructive 2D eye diagram showing the quality of equalized receiver eye in real time. The reason of our low bit error rate is now clear. The PHY's linear equalizer and 21-tap FFE and DFE have produced wide open eyes for data reception. This concludes our demonstration. Thanks for watching.